Hello, I'm Caitlin, and these are my best buds Madhava
Hello.
and Shika.
Hello.
We are presenting on behalf of Team Mind, which stands for Mental Illness Recognition through Neuroimaging and Deep Learning. Let's start with some statistics. In 2018, 1 in 5 adults, approximately 66 million people in the US, experienced a mental illness. In addition, with the ongoing COVID-19 pandemic in 2020, we've also seen an increase in the prevalence of anxiety and depression. With so many people affected by mental illness, the validity of a diagnosis is extremely important.
So, how does the diagnosis process work? Physicians will start by ruling out other underlying medical conditions. After doing so, the patient will be referred to a mental health professional where they will be interviewed about their behaviors, emotions, and other symptoms. Finally, the clinician will refer to the DSM-5, the standardized manual for clinicians in the US, to make the diagnosis. Despite the benefits of this process being standardized and fairly reliable, psychiatric diagnoses are limited by the poor understanding of the underlying biological mechanisms of disorders and are largely dictated by clinicians' discretion. Reviews of these criteria have found issues of both over and under-specificity, as well as a significant amount of overlapping symptoms, suggesting that boundaries are not as clear as they could be, and a high degree of heterogeneity or variability within disorders, which means that two patients with the same disorder could share none of the same symptoms. These factors suggest that criteria may not be as valid as we assume. On top of those limitations, the heavy reliance on the discretion of the clinician results in psychiatry and mental health systems having a higher potential for being negatively affected by implicit bias. For patients from marginalized groups, practitioners are more likely to underdiagnose affective disorders such as depression and bipolar and overdiagnose psychotic disorders such as schizophrenia. African Americans are 4 times more likely to be diagnosed with schizophrenia when compared to white patients. In addition, clinicians may lack cultural competency and be hindered by language barriers or stigma. Practitioner biases may manifest as over-pathologizing, where behavior of minorities is seen as unfamiliar and is interpreted as a symptom, or minimization, where genuine symptoms are assumed to be due to culture and are ignored. As a result of how bias manifests within the diagnosis of mental illnesses, we can observe large impacts such as the increased institutionalization of racial and ethnic minorities. In regard to the juvenile justice system, 50 to 75% of minority youth will qualify for a disorder due to the harsher disciplinary practices within their schools. In addition, despite only being 12% of the US adult population, African Americans make up 33% of the prison population.
In the future, the hope is to have more robust diagnostic criteria, potentially based upon neuroscience and other biomarkers instead of behavioral characteristics. Eventually, this may lead to the development of additional diagnostic tests using a patient's biological data. Before that can be done, however, the connection between biological systems and expressed symptoms must be established. This is what the RDoC framework from the National Institute of Mental Health aims to accomplish by studying mental functioning independent of current diagnostic categories and through levels of analysis, such as neurocircuits. With this in mind, our research is guided by the following question. Do neuronal biomarkers correspond to current classifications of mental illness? To find these kinds of biomarkers, we do not want to assume that the given diagnosis is automatically valid. Instead, we want to analyze patient data such as neuroimaging without being influenced by the existing categories. Given the complex nature of the data and that the patterns underlying it are unknown, we need to use a statistical approach that can independently learn from data and find unique features, which is where deep learning comes in.
First, we will train our deep learning models. To do this, the model takes the data we provide as input, processes it, and makes a prediction. The model learns to refine its predictions over time. Once we have a refined algorithm, we will use it to extract features from the data and cluster it. Lastly, we will examine the algorithm to identify activations on important parts of the data, which could be potential biomarkers. There are 2 types of deep learning algorithms that we will be using, supervised and unsupervised, and we will repeat the steps for each. In supervised learning, all the data being analyzed is labeled. In this example, we have images of pigs and not pigs fed through an algorithm or classifier that outputs predictions. The outputs are compared to the correct label, and based on the error, the classifier is improved. This is repeated over multiple iterations to get a refined classifier. Rather than pigs, we are applying the same process except to neuroimages, specifically MRI images. However, the effectiveness of our model is contingent on the validity of the labels, as any patterns that we will see will still be within the confines of the current clinical categorizations. Therefore, we turn to unsupervised deep learning, which can help find features independent of these categorizations. In this case, we do not require labels. As shown in the diagram, the images of animals are compressed to a smaller representation by an encoder, a type of deep learning algorithm. The compressed or latent representation captures meaningful features of the images. In our examples, those could be pointy ears or the number of feet. Then the decoder reconstructs the image from the important features. In our experiment, we will input unlabeled MRI scans into our unsupervised model for the purpose of finding important features within the neural structures. The final step of our research is comparing the results of the supervised and unsupervised methods to each other. For both models, we will run the algorithm to extract features and create clusters for comparison. Additionally, we will compare important biomarkers which are found by examining the algorithm of each model. We are making this comparison to see if there are any inconsistencies between the supervised and unsupervised models. For clusters, we will be comparing the clusters from both models to the traditional DSM-5 diagnosis to see if there are any biases in its diagnostic criteria. For biomarkers, we will be seeing if the two models look at different areas in the brain when classifying the same scan to see if disorders have distinct neurophysiological structure. We recently finished implementing a supervised classifier with schizophrenia and bipolar MRI scans. Using the classifier, we clustered the scans using a commonly used method called UMAP. On this cluster map, the pink dots correspond to schizophrenia while the purple corresponds to bipolar. As you can see, most of the data is separated along the diagonal, while there are also some subclusters within each disorder. Now that we have our supervised model, we will be working on our unsupervised model to complete the comparison. We are also looking into more datasets to make our model more accurate. Overall, we hope our efforts in biomarker identification and clustering can help advance efforts to address validity in mental illness criteria and reduce bias and misdiagnosis. Thank you, and are there any questions?